Hello everyone, I am Bernard Jin from FTC Team 17080 NewT.exe, and today we'll be doing a brief overview on drivetrains. So starting off, what is a drivetrain? The drivetrain is the part of the robot that actually moves the robot around on the field. It can be wheels, it can be legs, anything, and it generally defines the footprint of your robot. For example, if you have 3 wheels, then you're probably going to do a circular row. It's going to be probably going to be a circular design, while 4 more wheels probably means that it's going to be fairly rectangular. And it is the most ubiquitous part of a robot. It is part of every single robot in every single year, as there's yet to be a game where you can just sit where you start and do whatever. So, common considerations when designing a drivetrain. Starting off, are there obstacles on the field? For example, during Freight Frenzy, there was a barrier, and some drivetrains were designed, and you had to design your drivetrain to either be able to go over the barrier or around the barrier. Speed. If you need to move a lot, you'll generally want a faster, more nimble drivetrain, although this is inverse to torque. So if you're going to encounter a lot of defense or going to have to push a lot of things, you'll want to have more torque. Size, as mentioned before, during Freight Frenzy, robots had to get around a barrier or go over it, and if you wanted to get around, your robot needed to be at most 13 inches wide. And finally, defense and pushing power, which is a combination of both torque and grip. In games where the field generally isn't very cleanly divided, for example, in Power Play, robots had to move all over the field. You'll encounter plenty of defense. So if you're planning to either play defense or go against defense, you'll want a sturdier, more defense-oriented drivetrain. Starting off, we have Mecanum, the most popular drivetrain in all of FTC. Mecanum wheels are wheels with small rolls at 45 degrees, as you can see on the image on the left. And what this does is it allows for an omnidirectional movement, meaning that you don't have to turn the robot in order to move in different directions. For example, you can move sideways. It's a jack-of-all-trades drivetrain. It has a good balance of being speedy, maneuverable, since you're just replacing wheels. Since what makes Mecanum special is just the wheels, it's also fairly space efficient. You don't need any specialized mechanisms. And due to the huge variety of wheels, it's also fairly inexpensive. As mentioned before, there's a huge variety of wheels, so if you want it to be bigger or smaller depending on your robot or the game, or what material you want it to be made of, you have your choice. Unfortunately, because in order to move sideways, Mecanum drive wheels are designed to slip, it means that these types of drivetrains generally lack grip and pushing power. Usually this isn't an issue. Most of the robots you'll be running against will have Mecanum anyway. But if you're running against a robot that has traction wheels or treads, then you're going to have a hard time pushing them around. And there are variants of the Mecanum drivetrain, such as locking Mecanum and butterfly drive, which help fix the pushing power problem, but they come with their own issues, namely complexity and size. Next up, we have holonomic drive. Here we'll be talking mostly about X drive, which is wheels arranged in sort of an X. It's the image in the bottom right, as well as Kiwi drive, which is a holonomic drivetrain that has 3 wheels. It's on the image on the left. And there are wheels with small rollers at 90 degrees. So, which means that unlike Mecanum, where it's possible where some portion of the roller's roll goes in the direction of the wheel, for these, either the wheel turns or the roller turns. These allow for omnidirectional movement. Again, similar to Mecanum, you can move in any direction you want. And they allow for decent speed. They also allow for circular drivetrain mounting. So if you want to build a circular robot, so like a Roomba, you're probably going to go holonomic. They allow to use any number of motors that you want. ranging from 3 all the way to, if you want to include all 8 motors in your drivetrain, go ahead. Unlike Mecanum, where you're restricted to multiples of 4. And for this one, all you have to do is keep adding more wheels. Unfortunately, once again, because there are rollers and rollers are unpowered, they have not fantastic pushing power, and they're also fairly slow. Next up, we have the whole family of tank drives. Tank drives are probably what you're most familiar with outside of robotics. They use traction wheels to move, which are wheels that don't have rollers on them. Instead, they just have some sort of grippy material. They have extremely high pushing power and grip. They're also very fast because, again, there's no rollers to slip when you're moving, when you're trying to accelerate. And they're fairly simple to design and program. Unfortunately, they aren't omnidirectional, meaning that you're limited to only moving forward and backward, and you'll have to turn around if you want to move sideways. And the more wheels you have, the more space it's going to take up, which might make it hard to fit something like a DOM tree or other mechanisms into the side pods of drivetrains. Next up, we have treads. Treads, as the name implies, uses continuous treads to move the robot, and it has insane grip, as you have a huge surface that's in contact with the ground compared to just the tips of the wheels in other drivetrains. This also comes with huge pushing power. Unfortunately, they're very difficult to maneuver because you have a huge area that's touching the ground. When you try and turn, you'll have a lot of the treads are like dragging along the ground, making it slow to turn. They're large. You need a path to return the treads. They're oftentimes quite slow, again, because of the huge area that it touches the ground. Even though it can go forward and backwards quickly, it can't turn quickly. And finally, the most important one for FTC, they can damage the field, which could render your robot illegal to use in competition. And that's why, actually, there have been examples of specific treads in the past being banned. Because they were too grippy and would rip up the field when they were used. So tread lightly in this if you're using treads. Next up, into the family of swerves, we have coaxial swerve, where we have 4 independently turning traction wheels. The turning of the wheels is managed by a servo, while the actual spinning of the wheel is managed by a motor. And that lets you control them independently. So you have basically a traction wheel or tank drive, except that it can move omnidirectionally. They're very fast. Once again, because they don't have rollers, you don't have to deal with much slippage. And they have great pushing power, as well as omnidirectional movement. Unfortunately, compared to the other drivetrains, they are extremely complex. You have a bunch of moving parts. You have mandatory gears, and a huge bearing. And as a result, they're also quite big. They also take up a lot of ports on the control hub. To have a basic 4-module coaxial swerve drivetrain, you'll need 4 servos, 4 motors, and 4 sensor slots in order to tell where the wheel is facing. And also, they have fairly tricky kinematics. Because coaxial swerve isn't too common, a lot of times you'll have to derive the kinematics yourself, which, if you're confident with your math, go ahead. But if you're not so confident, this might not be the right choice for you. And finally, we have differential swerve. Differential swerve uses 2 or more differential-driven wheels. A differential is it's a mechanism that allows you to turn balanced 2 outputs based on 2 inputs. And because you have the choice of sending the power of both inputs to a single output, they allow you to be very fast and have a lot of torque. Because they also don't use tread wheel, sorry, because they don't use rollers, they're also grippy, which is pretty good for defense. Unfortunately, they don't have all right pushing power because a lot of the times differential swerves are only have to use 3D printed gears, and also that you only have two wheels that are powered. You'll have you'll be missing out on some pushing power compared to if you used 4 traction wheels. It cannot handle vertical curves because you only have 2 powered wheels. If both those wheels come off the ground, which, for example, if you're going up a curve, could happen, basically always happens. Your both wheels eventually lose grip, and you're out of luck. So these should only be used in flat fields. They're also difficult to program because you have to deal with the mechanical nature of the differential. And finally, they're fairly large, although this is offset by the fact that you only have to include 2 pods. So some tips for designing the drivetrain. First, keep in mind electronics, specifically hub placement and odometry wiring. For parallel plate drivetrains, which, as the name implies, uses sets of parallel plates as the side supports. For example, with this tank drive over here, you can often mount the hubs on the plates. Although if you're mounting other things on the plates, those might interfere with the wiring. If you don't feel confident that what you're currently designed to put on the robot is going to be your final design, feel free to add some extra mounting holes. Wider drivetrains that are wider than they are long generally turn better, although because they are wider than they are long, they're also generally a bit unstable, so you'll generally want to balance between them. And finally, FTC sizing boxes have a varying tolerance. So don't try and design all the way up to 18 inches. Design up to 17.5 inches at most to be safe. All right. Thank you all for watching, and feel free to take a look at our other videos for more tips and information about subsystem design.